My name is Egzon Miftari and I'm from the Visual Computing Group at Heidelberg University. This work has been done together with my colleagues Durstewitz and Filip Sadlo. As a motivating example, we look at the physical model of dry friction. A solid block lies on a rolling band. The block is attached to an air spring. As the block slides over the band, it will experience sliding friction. At a certain velocity, this sliding friction will transition into static friction, which is usually higher than sliding friction. As the deflection of the spring gets higher, the spring applies more force onto the block, which results in a transition from static to sliding friction. The block then moves towards the spring until it comes to a halt, and changes its direction again. This process involves discontinuous jumps between sliding and static friction. The state of the model can be expressed with the deflection of the spring and its time derivative. One possible dynamic system of this model can be seen here. By plotting the deflection against its time derivative, we can visualize all possible motions of this model through a phase-space diagram. As can be seen in the phase-space diagram, it displays some intriguing properties. Visibly, it involves a discontinuity. Streamlines can cross the discontinuity or slide on it. Furthermore, there is a region of transition between sliding and crossing. We now introduce stream sets on which we build our theory and technique. Usually, dynamic systems involve ordinary differential equations with continuous right-hand side. In the case of discontinuous right-hand sides, we need the theory of Filip systems, which generalizes differential equations to differential inclusion problems. The right-hand side is now set valued with the inclusion of the convex hull. Here, sigma ij is the discontinuity. Let us take a look at an example. The smooth vector fields of adjacent regions meet in a discontinuous manner at sigma ij. A closer look at the discontinuity shows how the convex hull is formed, which is here indicated by the green arrows. Due to the set-valued right-hand side, solutions to Filip systems are in general non-unique. Crossing flow occurs where one field points towards the discontinuity and the other away from it. A time reversal of solutions is here possible. Sliding flow occurs where both fields either point towards or away from the discontinuity. Furthermore, sliding flow can be of type repelling or attracting, and results in a continuous flow on the discontinuity, which we refer to as discontinuity flow. We now look at two initial vary problems and an attracting sliding flow. After some time t, the two trajectories intersect on a coinciding endpoint on the discontinuity. Since reversal of these trajectories is now impossible, we propose to associate the starting points through an equivalence class. With this we can view equivalence classes as points. Furthermore, we can define equivalence flow maps on these new points. These flow maps on equivalence classes fulfill the group properties, which implies time reversibility. Additionally, streamlines now generalize to stream sets. We now have a look at the interaction between stream sets and the discontinuity flow. For any given smooth vector field, we can extract its critical points, which are points at which the vector field vanishes. Through the Jacobian and its eigenvalues, we can characterize each critical point. The field points away from the red sources and towards the blue sinks. The green saddles are of hyperbolic nature and generate separatrices. These separatrices divide the field into regions of similar behavior. We can apply traditional vector field topology to the discontinuity flow. Here we look at attracting sliding flows with the saddle and the periodic orbit. We now compute the stream sets of these topological 2D structures. Black streamlines indicate non-unique flow. We can see that the separating properties of the 2D critical structures are inherited by their stream sets, which now separate other stream sets. In this section we investigate the impact of the transition between sliding and crossing flow. First, let us examine the involved structures. In these examples we find regions of crossing flow and regions of attracting sliding flow. These regions are always separated by boundary switch points or curves, which are the points at which one of the involved fields is tangential to discontinuity. These can be of type inbound or outbound. We can see in this example that the boundary switch curve indeed separates the crossing from the attracting sliding flow. At the boundary switch curve, the stream set changes dimensionality from 2D to 1D. Furthermore, the boundary switch curve induces a novel kind of separatrix and equidices, which are manifolds that separate regions of stream sets from regions of streamlines. These structures are consistent with time reversal, where the separatrix changes its type. Outbound boundary switch curves do not cause manifolds that display separating properties. Boundary switch curves of adjacent fields can intersect, causing twofold singularities. There are three different type combinations possible. In the inbound case, the separatrices and equitrices switch sides at the twofold singularity. The separatrix changes also its type. Together they highlight the amount of qualitatively different regions. The inbound-outbound case displays less separating structures. This is due to the outbound boundary switch curve, which does not induce separating properties. The outbound-outbound case usually results in dimensional blowup, which means that stream sets become volumes due to the interaction of the two discontinuities and the transitivity of the equivalence relation. We conclude this section with two basic cases of bounded sliding flow. Boundary switch curves can be closed curves like in this example of the bounded source, or they can intersect multiple times with other boundary switch curves to form closed regions of sliding flow, as seen in the example on the right. Discontinuities also impact traditional vector field topology in the smooth regions of the field. In this example we will see that sliding flow can bypass traditional separatrices. This field exhibits an attracting sliding flow and a 3D saddle. The saddle induces a separatrix, which separates two regions. Through the sliding flow, some flow can bypass the separatrix from one region into the other, negating the separating properties of the separatrix. The non-separating region is exactly bounded by the equitrix coming from the boundary switch curve. We now revisit the dry friction case from the introduction. The attracting sliding flow is bounded by an inbound and an outbound boundary switch point. The separatrix coming from the inbound boundary switch point re-enters the discontinuity, which results in a periodic orbit. The invariant sets consist of the source and one large stream set. We can extend the 2D model to 3D by making the airspring constant temperature dependent. Again, the system has one inbound and one outbound boundary switch curve. The stream set changes dimensionality at the inbound boundary switch curve. Therefore, the stream set consists of the states that result in the same state on the boundary switch curve. We presented an extension of the visualization of vector field topology to discontinuous vector fields, based on equivalence classes and stream sets. We introduced the topological structures induced by the discontinuity flow and the boundary-induced equitrices. Furthermore, we explored how these findings relate to traditional vector field topology. As this analysis was conducted on time-independent fields, the influence of time could be a subject for future research. Additionally, cases involving intersecting discontinuities hold significant interest. We thank you for your attention.